with method 1 using real notation. Here's our equation of motion. And here's our solution, and we're going to solve this equation by substitution. So essentially, we're going to find the first and second order derivatives, and then substitute for x, the first and second order derivatives in this equation of motion, and deduce expressions for the amplitude and the phase psi. So here's the first order derivative of the displacement with respect to time. The cos becomes a minus sine, the omega comes outside. Here's the second order derivative. The sine becomes a cos, another omega comes out, so we end up with an omega squared term. And then we can substitute into our equation of motion above. So here's the second order term. Here's the first order differential term. Here's the term in x, and here's our drive term. Now, this can be solved with some fairly lengthy algebra, and that's what we're going to do in the next slides. So here's that expression that we obtained at the bottom of the last slide. Now, we're going to need to expand out these terms involving cos omega t plus psi and sine omega t plus psi. And for this, we're going to need some trigonometric identities, and these are the two we're going to be using. So using those two identities to expand out the terms cos omega t plus psi and sine omega t plus psi, we end up with the following. Now, I've compressed into this expression a number of steps. I've expanded each of these terms, and then I've grouped terms together that include cos omega t or sine omega t. Now, the important thing to bear in mind is this expression is 0 at all times. Now, the only way this can be the case is if the coefficients of cos omega t and sine omega t, so the factors in brackets in each case, are 0 themselves. And that leads us to two equations. Now, let's consider the second equation. What we're going to do is divide the second equation by cos psi, and that gives us the following. So the sine psi divided by cos psi becomes tan. We lose the cos factor in the second term, we get another tan in the third term. And of course, we can immediately rearrange this to get tan psi. And this gives us straight away the expression that we had quoted in the last video. Now we can do something with the first equation. This time we're going to divide through by cos psi again. We end up with the following. We lose the cos term from the first. We lose it from the third term here, which I've written down here. We end up with the damping term, with the tan, and the force-related term, we end up with a 1 over cos. So here's that expression from the previous slide. Now we're going to use another trigonometric identity, and that's that we can rewrite 1 over cos psi as plus or minus the square root of 1 plus tan squared psi. So substituting for 1 over cos psi here, we obtain this expression. I've moved the force-related term over to the right-hand side here. You'll notice there's a common factor of a in all these three terms on the left-hand side. So if I divide through, I can get an expression for a, which is this. Now we previously deduced the expression for tan psi, so now I can substitute for that in this expression. And I obtain this rather complicated expression here. But if I multiply the top and the bottom by a factor k over m minus omega squared, then I obtain the expression for amplitude as a function of drive frequency that I quoted in the previous video.
But often one would could have a situation where there are many capacitors, and you can combine them in two different ways. Let's say either you place them in parallel, as is shown here. So we have a battery and three capacitors, 1, 2, 3. If they're combined this way, it's called parallel. And if they are combined the other way here, you can say in a row, they're called series, capacitors in series.